So, the next episode, we are trying to deal with another such frame, but loaded with a pointed load. The value of load is 12 kilonewton, loaded at point C. Automatically, reaction A here, because that's the only place there's reaction. Reaction A is equal to 12 kilonewton, so we don't need to bother ourselves calculating it because it's only one support that's carrying the whole load. So, and there's no support at C. So the reaction at A is 12 kilonewton. Now let's calculate bending moment. So now moment anywhere, put here, let's say E. Moment at C is 0, M at C is 0. Anybody who has been following this lecture must have known by now why MC is equal to 0. At E, M at E is equal to the load minus 12, which is the load, times the distance B, the EC, distance EC, which in this case should be 5 meters since E is in the center. That's times 5, perpendicular distance to the load. Hence, this angle is 90 degrees, the angle between the load and the distance. So, which means the moment at E is equal to 60 kilonewton meter. Then at B, M at B is equal to minus 12 times 10 is equal to 120 kilonewton meter minus 120 kilonewton meter. That's moment at B. Now, moment at F, M at F is equal to minus 12 times 10, because 10 is the perpendicular distance. 10 is the perpendicular distance from the load, from the distance from the load, 12 kilonewton. We're in BF now, but the length BF is not perpendicular to the load. That's why we are not multiplying with the length BF. Moment is force times perpendicular distance. So this is equal to minus 120 kilonewton meter. Then at MA, moment at A is equal to minus 12 times 10, which is minus 120 kilonewton meter. Simple. That is the value of the moment along the frame. I want to draw a diagram of bending moment. This is point A. This is B. So at C, the moment is 0. So and it is not a curve this time around, because if you check the former one we did, when it was loaded with a UDL, uniform distributed load, the equation was quadratic, and as such, the graph would be a curve. But this one is linear equation. If you look at there, you will see it. It's linear equation. So that's why it's a straight line. So here it is, at this point, it is 120 kilonewton meter. The same 120. Throughout, it's 120 throughout. So 120 there, 120 here. That's the bending moment diagram. That's the bending moment diagram. For this frame, 120 there, 120 there. So to calculate shear force at C is minus 12 kilonewton. 12 kilonewton. And so at 12 kilonewton, it is the same 12 kilonewton up to B, up to point B. Shear force is 12 kilonewton throughout that line being to C. So diagram of shear force. $12 kilonewton. 12 kilonewton. Shear force. That's the diagram. The same shear force. It didn't change because the force was not changing, unlike the UDL that was varying because of distance. Now let's deal with normal force. The normal force will occur in AB, in member AB. That's where normal force will occur, in member AB. And that is still a what? 12. There's no normal force in BC because the force is across the member BC. But the member BA is not across. It moved through the member. The force moved through the member. That's why it's like a column. It became a normal force. So if I'm to draw the diagram, $12, that is the normal force. So shear force, normal force, bending moment. So these are the stresses that we've been able to analyze the frame loaded with a pointed load. The first one we did was loaded with a UDL, a pointed load. So that's the end of this episode.